Hello, and once again, welcome to yet another session on inorganic salt analysis. This is a very, very important topic which mostly is neglected by students, thinking that these are to be studied these are to be done in practical classes. Welcome, Rudra.
Pranam, sir.
Namaskar, Anil sir. Now, this topic that we are going to discuss today is actually the theories behind practical, inorganic practical salt analysis that you do in your practical classes. But you have to prepare them for your competitive tests like JEE, IIT, NEET. You will definitely get a number of questions from this topic. What we commonly say, salt analysis. In fact, what is being discussed in this +2 level, 11 and 12, in India, in general and Odisha in particular, is not an ideal situation that is to be followed. It is a case of systematic analysis. That means you are given a mixture of at least two salts, means two cations and two anions. Salts, usually ionic compounds, or they are soluble in water, split into positive and negative ions. Some of them are sparingly soluble or so-called insoluble. We have to devise methods how to detect the positive and negative ions for sparingly soluble substances, for example, silver chloride. We will be not discussing the analysis of sparingly soluble substances, but it can be done. We will discuss in our program, we will discuss how to even detect the positive and negative ions in sparingly soluble substance like silver chloride, like lead chromate, like barium sulfate. Now we'll be doing in two parts. One is the detection of anions, which I will be delivering without asking you to write anything, or I won't write anything. They are so simple that you will be revising with me how you categorize different anions into three different classes. Systematically you analyze and eliminate the possibility of one group before going to the next group. Let's start. Now let us start the discussion. You are given a salt. Usually in +2 level you are given a white salt, but you should study everything for a colored salt involving transition metal salts, which are usually colored. You already know which transition metal salts or compounds are colorless, D0, D10, or those which absorb in the UV region. So most of the transition metal compounds, they're colored. So you are not given in the practical a colored salt usually, but you must study everything theoretically, how to detect the positive and negative ions. So let us go for negative ions first. Now the first category is the dry tests. Without preparing a salt solution, maybe water extract, or I will tell you about sodium carbonate extract, nothing. Take a pinch of the salt. First, take a test tube, add a bit of dilute acid. This category is the gas evolution reaction. The gas evolution reaction in using a non-oxidizing dilute hydrochloric acid or dilute sulfuric acid. Sulfuric acid is very safe because hydrochloric acid contains a very good reductant chloride ion. So in dilute HCl, these metal ions, these anions won't have any response to chloride ion. So either you can take dilute hydrochloric acid or sulfuric acid, not nitric acid. So under this category, you have several anions. Let us not bother about the cations now. Carbonate, sulfite, sulfide, nitride, thiosulfate, acetate, and of course oxalate. Of course, we can include, no, oxalate will be included in concentrated sulfuric acid category. I'm sorry. Carbonate will produce carbon dioxide, you know. And you know how to detect carbon dioxide. It is a colorless gas, odorless gas. So lime water is used to detect it. You pass that gas through lime water, which is calcium hydroxide solution. First you get a milky white precipitate, and then you pass the gas in excess. You will find the milky white precipitate will dissolve, forming a soluble calcium bicarbonate. This you know from class 8. That's the reason why I tell you we will be finishing the acid radicals or the anions in haste, in fast pace. Then I will start writing something and you will be also joining with me to write about separating the cations in the 6 groups and then taking each group and analyzing separately. Now, sulfite produces SO2, burning sulfur smell. The smell of sulfur dioxide is very typical. It's called burning sulfur smell. You can pass that gas through acidified potassium dichromate. You find the orange color turns green. I have not balanced the equation. You can balance by any method. You know, there are multiple methods known to you how to balance a redox reaction equation. Sulfite gives a rotten egg smelling H2S gas. These are all non-redox reactions, but yes, the test that you carry out sometimes is redox. For example, SO2 is confirmed by passing it through some good oxidizing agent like acidified potassium dichromate. That's a redox reaction. Now the H2S, the rotten egg smelling gas that comes out, I have not written here. It is so very common that rotten egg smelling gas, if you sew a filter paper or a piece of paper soaked in lead acetate solution, that paper turns black because there is a double displacement reaction forming lead sulfide. So, and the most important test is adding sodium nitroprusside solution. If you know, not adding, in fact, if you pass this H2S gas or any sulfide salt, including H2S, any soluble sulfide salt to sodium nitroprusside solution, which is a complex of iron plus 2 complex, pentacyanide nitrosonium. In fact, it is not nitrosyl, it is nitrosonium or nitrosilium plus 1. Iron 2, ferret. Sodium pentacyanide, nitrosonium, iron 2, ferret 2. And when you treat the S2S gas or any sulfide to that solution, it turns purple. This is colorless, but it turns purple because sulfide is attached to NO, forming NOS ligand, which has a charge -1. Because NO is +1, sulfide is -2, so altogether the NOS ligand is -1, and now the formula gets changed to Na4 FeCN5 NOS. Iron remains at +2. So, NO is a non-innocent ligand. Non-innocent means it is a culprit. That means some redox reaction happens not with the metal ion, but also with NO. It donates electron, it can accept electron. So if the ligand takes part in the reaction, then that ligand is not innocent. And it's called non-innocent ligand, which takes part in a redox reaction along with the metal ion. So that happens. Sulfite, you can also have another test that is given in your NCERT book. This is also possible, but there's no need since I also was checking what other tests that your NCERT book is giving in Unit 7, Salt Analysis chapter. So I was getting this very simple test when a sulfide salt solution is treated with barium chloride. Barium chloride, in fact, is not used for detecting sulfide salt. It is used for sulfate. So there will be a confusion. Yes, barium sulfite is also a sparingly soluble substance, but the difference is barium sulfate is insoluble in everything. In concentrated HCl, in nitric acid, it is insoluble. But sulfite is easily soluble. Again, it produces the same SO2 gas. And that, if you don't do that, if you straight away add some acidified potassium permanganate or dichromate, there itself the color, purple color decolorizes because the SO2 doesn't go up. The SO2 produced with the acid with sulfite is cut by the oxidant and is being converted to sulfate ion, and the color and manganese from +7 to +2, and it decolorizes. Animes Samant, good evening, is watching, is very important. Animes usually students neglect. That is why I thought of, making you serious. Everything you know. Maybe you will be getting a benefit from the discussion on cations, metal ions for higher level thinking skills, which in your syllabus, they have made it very simple, made easy way in NCERT, surprisingly, they have stipulated for one salt. The entire systematic analysis that you find in +2 level, anywhere in India, you will not find a real systematic. In the name of systematic, they give only one salt. But the description is for systematic. How to remove, separate. I use the term separate group 1 metal ions by making a precipitate separate from the solution. Same solution, you will be given only one solution, not 2 times, 3 times. From that solution, group 1 metal ions are separated as some precipitate, then group 2. Then it is kept separately until group 6. Then you start group 1 precipitate, uh, then analyze what are the different ions which could be there. So this is valid when at least we have 2 salts, 2 cations, 2 anions. If you are having 1 cation, 1 anion, a single salt, so what is the reason why you should learn to separate group 1, group 2, group 3, group 4? There is no need. It is a mockery at the study of salt analysis. There is no need to use common ion effect to suppress the dissociation or suppress the precipitation. I'm sorry, suppress the precipitation of some other metal ions and selectively precipitate out a particular group metal ions. So that comes into force when you have at least two. One group is in group 5, the other one is group 2. So you separate group 2 because that will interfere. If it will be there, not separated, it will interfere when you come to group 5. So therefore, the forefathers of analysis, they have systematically analyzed putting the common metal ions into 6 groups. So you have to first separate 1, 2, then 2, then 3, then 4, then 5, then 6. 5, 6, then finally 6. That we study, but we don't do straight away. There is no need straight away. Supposing you have calcium, there is no need to add ammonium chloride till saturated, ammonium hydroxide till alkaline, ammonium carbonate, and then get carbonate precipitate. Straight away you can add ammonium carbonate. There is no magnesium to interfere. It is only calcium. So, but we shall study. In a proper perspective, we study. Now, why the color of permanganate is discharged? Because SO32 minus, doesn't produce SO2. In C2, SO2 minus is converted to SO42 minus, manganese from +7 to +2. So the color, permanganate color, bleached, discharged. Now, nitrite is a very typical salt. Nitrite salt produces two gases, NO and NO2 together. Because HNO2, in fact, we can write in a different way. A double displacement will give you HNO2. That HNO2, disproportionates to NO and NO2. Without doing that, I have straight away in one equation, I have shown NO2 and NO. And you can detect NO by using a paper, a filter paper, or a paper soaked in ferrous sulfate solution. And that solution turns brown. This is the equation for brown ring test. I'll tell you how. Just wait. But in your book, NCERT book, this test for NO is not given. NO is a colorless gas. But actually you will be getting a reddish brown. The observation is that any nitrite salt with any dilute non-oxidizing acid like sulfuric acid or hydrochloric acid will produce a reddish brown gas, NO2 gas. But there will be hidden NO colorless gas. That is detected by this one, ferrous sulfate, which will turn brown. But in your book, they have detected NO2. That is passed through, or you take a paper soaked in potassium iodide and starch and show it to that gas. The NO2 will oxidize iodide to iodine, and iodine with starch forms a blue complex. That is a starch transfer complex, iodine to starch. Due to CTS, charge transfer spectra, you get a blue color. Starch and iodine forms a charge transfer spectra, and for that it looks blue but absorbs its complementary color. Can you tell me which is the complementary color that the starch iodine complex absorbs, so that we get the color blue? Rudra, you just think of that color wheel that I have told you.
Sir, red and yellow.
I remind you, very recently we talked about the color. How you know this is V? Indigo is deleted, VBGYOR. So if we are looking, it is looking blue, then it is absorbing what?
Sir, orange.
Huh?
Orange.
Yes. But you were telling what?
In between yellow and red.
Yellow and red is orange. So you must tell exactly orange. You understood?
Yes, sir.
So it looks blue, but it absorbs orange. Therefore, it looks blue. Now, alternatively, yeah, that's what I have written here, and I have written same thing here. Salt solution, directly you add Ki. Instead of, making a potassium starch iodide, potassium iodide and starch paper, or passing that NO2 gas to a Ki solution, you can salt solution, directly add Ki, directly add some starch solution and bit of acetic acid. So there, in situ, the NO2 would go up, NO will go, NO2 will remain. NO2 will oxidize Ki to iodine. Iodine will form a complex with starch and the solution will be blue. The other one is very interesting. The same nitrite, it's the same, you have to, detect nitrite. What you do, you take salt solution, this time a bit of acetic acid, and you add sulfanilic acid. Sulfanilic acid is nothing but para-amino benzene sulfonic acid called sulfanilic acid. So in the beginning, nitrite salt with dilute acid has to be added, acetic acid is there. So it will produce HNO2. HNO2 is unstable, no doubt, but immediately it will form a diazonium salt, parasulfonic acid diazonium salt. Sometimes water will be found in left side. So if you cannot judge that, it is best to go through or via the ionic equation. That will give you the correct, description of the happenings for ionic compounds. Now, acetate ions are rarely given, but yes, in dilute sulfuric acid, it produces acetic acid. And if you slightly heat it, it will produce a vinegar-like smell, and that will turn blue litmus red because it is acid. Now, you can also confirm the presence of acetate salt by ester test. Treat it with ethanol or any alcohol in Kong sulfuric acid and heat it. You will find ester formation. If it is ethyl alcohol, it is ethyl acetate. And the typical smell, as you know, for esters is fruity odor. Fruity. It's a typical different odor that you will not find in any other aliphatic compounds. Fruity. Fruit-like. Or, this acetic acid that is produced, the salt solution with, of course, neutral ferric chloride, because ferric chloride contains a lot of unreacted HCl. So that has to be first neutralized by base, then added. Then it will get a red color. In fact, salt solution with sulfuric acid, that's acetic acid, any carboxylic acid produces a red color with ferric chloride. And that red color, a I'm sorry, a reddish brown precipitate is due to this complex, dihydroxydoacetato iron complex, iron 3 complex. You can take directly salt solution. You need not add sulfuric acid. That acetate complex will be there. But any carboxylic acid also will give you a reddish brown precipitate with ferric chloride. That's what I want to say. You will get, because ferric chloride solution is acidic due to salt hydrolysis. It will be protonated and you will get acetic acid. And we need acetato ligand, hydroxido ligand, right? So that you will, with hydroxide you will get from water, you will get this. Now coming to, yes, I have written the entire equation, balanced equation, acetate directly. There is no need to protonate it, acetate ligand, and water will produce hydroxido ligand and H plus will come out as the other product, and this is the complex. Hexacetate, this is not correct. This is hexacetate. Hexacetate, no, this is correct. If it is a brown precipitate, this is only monoacetate. I am so sorry. It is correct. But if it is a red solution, if you are adding more acetate ion, excess, then you get hexacetate. But if there is water, if you just take that red solution, yeah, it will produce first the red solution first. Here, I have written here, this is the red solution, this one. Then if you boil that red solution is this, hexacetate. Then when you boil it, it will become this. Hydrolysis will occur, and this is Fe3. I'm sorry to tell you, this is Fe3. The red color is due to Fe3, OH-2 hexacetate, not Fe. I'm just getting little distracted. I'm sorry for that, because I'm looking at how quickly I will finish this and come to metal ions. Now this is Fe3. It is a trinuclear complex, Fe3OH-2 hexacetate. That's what I was wondering, how 6 acetate ion will be shared by 1 iron. There will be 3 iron, and then that is red solution. But on boiling, they will be separate out. It is a mononuclear complex. FeOH-2, 1 acetate. So this is red-brown precipitate. This is all about acetate. We cannot spend so much of time for one. Then second category. First category is treatment of the salt. Dry salt, I mean not making a solution. These are called dry tests with a 1 milliliter or maybe 0.5 milliliter or say 1 cc of dilute acid. A pinch of the salt. If dilute acid does not produce any effervescence, you see there is no gas bubble formation. Even on warming also there is no gas bubble formation. Then you are sure carbonate, sulfide, thiosulfate. Oh, thiosulfate I missed out somewhere. Yeah, thiosulfide is a cousin sister of sulfide. It will produce same SO2 but a yellow sulfur, colloidal sulfur precipitate. I mean yellow colloidal sulfur. Along with SO2, same potassium dichromate. So thiosulfate and sulfite, they behave similarly. So they are under one category: nitrite, sulfite, thiosulfate, carbonate, acetate. These belong to one category. If you fail, then go to second category: treatment with conch sulfuric acid. Take 1 cc of conch sulfuric acid and add a pinch of the salt, and you have to heat. By default, you have to heat. And these contain 5. Remember, this category contains chloride, bromide, iodide, and nitrate. Don't write anything. I'll give you the file. Just try to understand. So if it is chloride, then you will get HCl first. And if you take a glass rod and dip it in concentrated HCl solution, concentrated ammonia solution. This is a rod dipped in conch ammonia solution and sow to the HCl gas. The HCl is colorless, but when you sow ammonia gas in a rod, glass rod dipped in ammonium hydroxide, and there will be dense white fumes. You must have done. I wonder nowadays students are so very busy for their NEET and IIT, JEE tests. Even they don't do any practical act in their respective schools. Please correct me if I'm wrong. If I'm wrong, I withdraw unconditionally. I'm sorry. And then you add manganese dioxide, the black powder there itself. Either you can write down MnO2 plus NaCl plus sulfuric acid. So instead of HCl going up, the HCl is oxidized by a good oxidant MnO2 to produce chlorine. I have done in steps. The HCl which is produced, it also oxidizes some of the bromide to bromine. You can directly write from NaBr or from HBr. You can write NaBr plus H2SO4 conch You can write down bromine SO2 plus Na2SO4 plus water. But some HBr is also produced. Why? Because when you add MnO2, the red color, the bromine has a red color vapor that is intensified. The intensity of the bromine color is increased quite a lot because there were some HBr coming out, but that HBr won't come out. For this, you can write out directly MnO2 plus NaBr plus H2SO4 heat, and I am writing down here it is Mn. You can write down MnSO4 plus Br2 plus sodium sulfate plus what? I'm not balancing it, please. So the bromine color is intensified because MnO2 is a strong oxidant, doesn't allow any bromide to produce HBr, directly produces bromine vapors. So bromine vapor, you can see red color. Your eye will not see it. But still you can use supposing you are color blind. I'm sorry, just supposing you can't detect red color. You can detect only blue color. Then take starch iodide solution paper and show it. Bromine plus starch iodide will give you iodine plus starch bromide. That iodine with excess of starch will produce ACTS, which is blue. The same blue color you will find here. Now, iodide, you don't need starch iodide. Iodine will come and you need to take that equation. What happens here? See, nitrate salt produces nitric acid first with sulfuric acid, double displacement. Then that nitric acid oxidizes ferrous sulfate. When you add freshly prepared ferrous sulfate, it is oxidized to ferric sulfate and nitric acid is reduced to NO from +5 to +2. So this NO is required because one of the ligands is NO. So ferrous sulfate is used as a reductant to reduce nitric acid to NO, and that NO along with water, because ferrous sulfate always remains as hexa-aqua complex. So there is a ligand displacement reaction. One aqua ligand is replaced by NO. So the brown ring is nothing but penta-aqua nitrosonium. Previously, it was thought that it is a neutral nitrosyl ligand and iron is in the +2 state like ferrous sulfate. But after long time checking the magnetic property and other parameter spectroscopic property, it was revealed that iron is not in +2 state. Very interestingly, it is in the +1 state. And NO is in +1, nitrosonium. So brown ring is penta-aqua nitrosonium iron 1 sulfate. And remember, which is not given in your book, that nitrite salt, which we have done so extensively in dry test using sulfanilic acid and then one naphthyl amine and then forming an azodide. Those discussions in the dry test that can also be used for brown ring. Brown ring also, because the nitrite will give you this nitrous acid, that also will oxidize ferrous to ferric and itself reduced to NO, and same brown ring will be produced. So remember, not only nitrate gives, that is there in your book, but also nitrite salt gives the same brown ring test. You may ask me now, then how, if nitrite and nitrate are together, how to test nitrate? So that is done in a higher class. The interfering radical, this nitrite and nitrate, both will give brown ring. So you have to kill nitrite ion by using something. Some is an alloy called Devardas alloy with magnesium and other. There that decomposes nitrite to produce nitrogen gas. So before going for brown ring, you have to kill nitrite. By using some alloy, we kill nitrite ion. Nitrite ion is already tested in dry test. And it is confirmed also with a dye formation test, sulfanilic acid and naphthylamine. And then if after killing nitrate salt, if you get positive brown ring test, then definitely it is due to nitrate ion. So this interfering radical test we are not doing today, or you are not supposed to get. Then how to test sulfate? Sulfate ion was not there in the dry test category. It is only tested in the wet test. Make a solution. Wet means not WEIGHT, which is a colloquial, term for mass. We mean mass, but we say weight. It's not that weight. It is weight. Means weight. Pani de pani, solution. So we prepare a solution of the salt and then add barium chloride solution. Yes, barium chloride is not meant for sulfite. It is meant for sulfate. Yes, barium sulfite is soluble in dilute acid, but barium sulfate is such a white precipitate, it is insoluble in conc HCl, conc nitric acid, nothing. Even on boiling also. But barium sulfate is soluble in lead acid. Now, then what do you do? This sulfate solution, direct original solution OS, can be treated with, instead of barium, this is an alternative test, or instead of barium chloride, you take lead acetate. Lead sulfate is also white. These are the two tests for sulfate ion. Then phosphate ion, PO4 3 minus. So that is called, and I used to tell students to remember this test as ammonium molybdate test. Ammonium molybdate is a colorless solution, NH4 whole 2 MOO4. This is a very famous reagent called ammonium molybdate test. Guys, why you are sitting with me today? And large number, I find large number are also watching directly, and many more after that, after my class. It's because these things which I'm taking up at the end, towards the end of your class 12 program, are not really taken seriously by students, but you miss marks. Once I discuss, it comes to your mind, yes, this is that, this is that. So let me read. This is so easy. So you feel encouraged to study and prepare for your competitive examination. So ammonium, what you do, take any phosphate salt that is given to you, for example, add first few drops of conc nitric acid, few drops of concentrated nitric acid, and then excess of ammonium molybdate, and stand it for some time. You get yellow precipitate. We call it canary yellow precipitate, canary yellow. Yellow precipitate, that is called ammonium phosphomolybdate. And to write the equation easily, I used to say NH4 whole 3 PO4 ammonium phosphate dot 12 molybdenum trioxide plus 21 ammonium nitrate. This is a balanced equation. 12, 24, this is 1, this is 21, 3 and 12. But actually, it is phosphomolybdate it is ammonium phosphate. In each O of PO4, the O is replaced by MO3O10. So this unit, MO3O10, replaces O. O. The O. This 4O are replaced by, each O is replaced by MO3O10. So altogether, MO12O40. In some books, you will find NH4 whole 3 PMO12O40. Or I used to say, to remember this, 12MOO3. Or you can say PMO3O10 whole 4. This is called ammonium phosphomolybdate, which is yellow. Test for phosphate. You will find similar will be the test for arsenate. Arsenate and phosphate, they have similar test. Same, instead of this one is phosphorus here. Yes. Instead of phosphorus, it will be arsenate, ammonium arsenate dot 12 molybdenum trioxide, or ammonium arsenomolybdate. Arsenomolybdate. I will talk about that later. Then another test for chloride, bromide, iodide. This is wet test where you prepare a solution first. Chloride will give you, if you add silver nitrate solution, you get a white precipitate, curdy white precipitate, which will dissolve in ammonia solution, forming the diamine silver chloride. And of course, if you add nitric acid, dilute nitric acid to this colorless solution, you will get back silver chloride. Back again, I will discuss about that in our cation analysis. Sodium, any bromide salt will give you silver bromide, which is yellowish white. This is completely white. This is yellowish white. And that is not soluble in dilute ammonia, but concentrated ammonia, it will be soluble. But silver iodide from an iodide salt will be completely yellow, deep yellow, and it is neither soluble in dilute or concentrated ammonium hydroxide. So this is the way you can distinguish between chloride, bromide, iodide. Thinking that you have got one salt, but if you are all the three salts will be together, then what you do, you first get silver iodide, slowly add silver nitrate, because you know the KSP, the solubility product of silver iodide is the least, say 10 to the power minus 40. So that is exceeded, the ionic product exceeds, or the Q, the reaction quotient, here we call ionic product, exceeds the KSP of AgI first. So you get yellow precipitate first, then you filter it out. Slowly add more and more silver nitrate. You will never ever find white precipitate. Students in higher level, we mix up chloride, bromide, iodide. Three salts we give to a undergraduate students. Say sodium chloride, potassium bromide, and say lead iodide. Lead iodide is sparingly solved. Say some iodide, say calcium, strontium iodide, whatever we give. So all the three halide ions are there. So how he or she will distinguish, I mean, detect all the three. So systematically he has to go. Chloride will come at the end. So after adding a lot of silver nitrate, you will get, slowly the yellow color will fade. It will become yellowish. Then yellow color will go. You will find nothing has happened. Chloride is not there. You will be bored. Simply you will be bored. You will say, no, only iodide or bromide or both are present, no chloride. But if you have patience, continue to add silver nitrate, you will find white precipitate will come very, very late. Because KSP of silver chloride is only 10 to the power minus 10. While that of silver bromide is less, maybe I'm just telling a fictitious value, say 10 to the minus 15, and silver iodide is 10 to the minus 40, for example. I don't remember. So it comes one after the other. Now there is another test. I'll tell you how elegantly you can first detect fluoride by this unique test called chromyl chloride test. And then iodide and bromide, if they are present together, first you have already detected chloride. Then iodide and bromide together can be detected by another test. I'll tell you now. That is there in your book. Chromyl chloride is also there in your book. So take the solid salt, add some solid orange color potassium dichromate, and add some concentrated sulfuric acid heat. You will produce a very polluting vapor, a orange red vapor. Be careful. Don't let loose to the air. You try to take it in a delivery tube and put it in a sodium hydroxide solution, alkali solution. So this orange red color vapor is nothing but chromyl chloride. Can anybody remind me in organic chemistry where this chromyl chloride is used? Yes, Rudra? Or anybody watching from the YouTube? Write down in the chat box. Chromyl chloride is used in which organic reaction? Yes, Rudra?
सर ऑक्सीडाइजिंग एजेंट सर ऑक्सीडाइज करे अल्कोहल को.
Are you kidding me? Yes, I am waiting for any guy or a girl watching from remotely to write down in chat box that chromyl chloride is used for a very simple, the preparation of a very simple compound in organic. Avantika, are you still there?
सर
Yes, try. Hmm.
सर जो बेंजाल मैंने
So you are talking about the intermediate, the chromium intermediate. But what is the reactant that you take and what is the product you get using chromyl chloride? I'm not asking about the intermediate. Yes. You either study the chemistry of toluene or study the chemistry of benzaldehyde. Now, can you tell me what is
Yes,
the name?
yes.
What is the name of the reaction? Toluene is converted to benzaldehyde by using chromyl chloride. What is that? The name of the reaction? Hmm?
Sir, ITAD?
Yes, ITER reaction. So, because you are studying chemistry, physics, mathematics, and some guys are who are medical minded are studying botany, geology. So you are not able to hold so many things together. Yes, it is. It is the ITER reaction. Okay. So you are getting yellow color solution. That orange vapor reacts with NaOH to form yellow solution. This is sodium chromate. You can also confirm the chromate ion formation by adding lead acetate, and that will give you lead chromate, which is a yellow PPT, precipitate. This will confirm the presence of chloride. Now, another test that is called chromium 6 pentoxide test for chloride. So after chromyl chloride test, this sodium chromate, instead of adding lead acetate, you can add hydrogen peroxide solution 10% by volumes hydrogen peroxide in acidic medium, and give some organic substance, organic solvent, which will remove chromium 6 oxide. This amyl alcohol is given when, we have studied in the chemistry of potassium dichromate and also the chemistry of hydrogen peroxide. The first step, dichromate, will give you CrO5. If you don't have any organic solvent to remove it, to dissolve this, the diperoxide, then CrO5 will decompose to produce Cr plus 3, and then oxygen gas will evolve. Otherwise, you don't get oxygen gas. Instead, CrO5 will be dissolved in amyl alcohol. If you shake it, and that amyl alcohol phase will be looking blue color. So this is another test which is done after chromyl chloride. You get the yellow solution. Then that yellow solution, you add hydrogen peroxide with some sulfuric acid and amyl alcohol. And this reaction, the first step, chromium 6 pentoxide. It's not chromium 10. Chromium can never ever go to 10. It has 4s1 3d5. Max is plus 6. So it is 6 pentoxide. So that is. Now, coming to fluoride is not there in your course. Fluoride with Kong sulfuric acid will give you HF. HF, then what you do? Take a glass rod, dip in water and show it to that HF vapor. First, the double displacement will produce silicon tetrafluoride, and silicon tetrafluoride will react with water to produce silicic acid, which is white turbidity. That water droplet sticking onto the glass rod will be opaque, will be white. It's called turbidity, white turbidity. That will indicate the formation of silicic acid, orthosilicic acid, and that is the test for fluoride. So, oxalate can be also confirmed by adding calcium chloride, so that you get calcium oxalate, which is a white precipitate, which is insoluble in acetic acid and also insoluble in ammonium acetate and oxalic acid. And if you take that precipitate and treat it with dilute acid, you get double displacement forming oxalic acid. And then you add potassium permanganate solution, acidified potassium permanganate solution, then the redox reaction with oxalic acid will produce carbon dioxide bubbles, and the purple color of permanganate will discharge, and the CO2 can be tested by lime water test. Are you following?
Yes, sir.
Now, I was telling interfering radicals. Now, sulfite and carbonate both give lime water test. SO2 produced from sulfite, carbon dioxide produced from carbonate, both produce lime water, give positive lime water test. Then if both are present, for example, then how to detect? Sulfite can be easily known because the smell of the gas is typical, burning sulfur smell, not colorless. Not smellless. But if carbonate is also there, it will be difficult unless you kill sulfite ion. I was telling you how to test nitrate ion in presence of nitrite. To kill nitrate ion by using some alloy and then test for nitrate. Similarly, you add in the solution, you add acidified potassium dichromate. And if you find the gas produced, still the gas is produced, and that is a odorless gas, and that turns lime water milky, and the solution becomes green because SO2 cannot fly. It will be trapped inside, or else you can write down sulfite itself directly is converted to sulfate and chromium from +6 to +3. So the orange color of dichromate turns green, and no burning sulfur smell comes out, but gas comes out. Lime water turns milky, then it is definitely carbonate. And the green color confirms that there was also sulfite. So both carbonate and sulfite can be detected in one experiment. Adding potassium dichromate solution, acidified potassium dichromate solution in the salt mixture, and then the evolving gas passed through lime water. Here it will be milky, and here it will be green. Now I was talking about chlorine water test, which is there in your book. Chlorine water test is used to test both bromide and iodide together in presence of each other. But in your book, it is given separately because the entire creation of that course, NCERT course, is for one salt. So it's not given together. For bromide separately, from iodide separately, but we will be studying together. But same equations will be same. Now, take the salt solution, add some organic solvent like carbon tetrachloride, chloroform, carbon disulfide, or methylene chloride, some organic which will not be soluble in aqueous solution. They will form separate phase. They are immiscible. Then to that, add slowly dropwise chlorine water, which is an oxidant, and progressively sec it. Sec it thoroughly and see what color comes out. Then add further chlorine water, sec. You will fast. You have to sec and then stand. Well, these two phases will separate. Organic phase and the aqueous phase will separate. Then you will find in organic phase, it will be colored violet in the carbon tetrachloride layer. Because iodine, although in water forms a reddish brown color, but in organic phase, it will, in iodine is always a charge transfer happens. But in carbon tetrachloride or in organic solvent, no charge transfer happens. So the color remains as a virgin color, iodine violet. So the color of the solution, which is iodine, is more soluble in organic solvent being a nonpolar solute. So that violet color will be produced. Then you continue to add. In your book, it is over. Violet color means iodide. But what I say, two anions are together. First, you are detecting iodide by forming iodine, which is violet color, to the organic layer. Then you continue to add more chlorine water. Then slowly, the iodine will be further oxidized to iodate from 0 to +5. Okay? Then once it becomes colorless, you add, continue. Don't be disheartened. You add, continuously add more and more chlorine water, dropwise. Then you will get a red color. Because bromine will finally come out. The moment all iodine will go, all iodine, oh, this is iodine, I'm sorry. All iodine will go as iodate ion, it becomes colorless. Then bromide turn will come and will produce red color bromine. That organic layer will be turning red. But in your book, only red for bromide and violet for iodide. That's it. So only bromide, I have just, from your book, I have said bromine organic layer red, iodide organic layer violet. But systematically, First bromide will be detected. First iodide will be detected with violet color. Then the violet will vanish, forming iodate, and then bromine will come from bromide. This is all about the story of negative ions, all kinds of negative ions, and you will definitely make a note for your competitive tests or for your board examinations or both. Now the interesting things comes. Before we go for the metal ions, wet test, systematic group analysis, let us quickly complete the dry test. What is a dry test tube heating? You get a lot of information by heating the salt in a dry test tube. Like if it is a hydrated crystal, then water of crystallization will come out and deposit at the cooler part. If it is a nitrate salt, it will decrepitation sound will happen. Some alkali metal salts will melt at the test tube. So some information you will get by simply heating salt in a dry test tube. Or the change of white color changes to yellow. For example, the zinc salt, lead salt, they will turn to yellow, and on cooling it becomes again white. So this information you just record. Then go for, now in dry test tube heating, I have borrowed this table from your book. It becomes blue when cold, but white when hot, it is copper. That means copper sulfate dot 5 water. It is blue. It hydrated. The water goes, means it becomes anhydrous, becomes white and remains white. Not turns green, but it becomes dirty white or yellow. It is ferrous. White becomes yellow. Zinc becomes white, yellow, and when you cool again white. It's not written. I'll tell you later. Pink, cobalt, it turns blue on heating. So this is simple observation. Then charcoal cavity heating test. Now in your book, there is a little bit of confusion. It is talking charcoal cavity test, means it is talking about charcoal reduction test. But charcoal cavity is used for cobalt nitrate test as well as charcoal reduction test. So I have made it simple by making charcoal cavity heating test. First, you have to diagnose. Just like you have a disease, a doctor is, asking you to go do for blood analysis. Some tests are coming. So if this is this, the disease is this. If you have this, disease is this. So the diagnosis the doctor is making out of the blood test report. So here charcoal cavity heating is used as a diagnostic test for proceeding to different individual category. For example, no, what you do, you make a cavity in the charcoal block, you make a cavity, a hole. Then add some salt, add some fusion mixture. Fusion mixture is sodium carbonate and potassium carbonate mixture is called fusion mixture. You need some carbonate. We'll know why. And then charcoal cavity, you put it inside the charcoal cavity and heat it in an oxidizing flame. Use a blowpipe, be a goldsmith. If the Bunsen burner, the holes are open, air is going, so you are getting oxidizing flame or non-luminous flame, you heat for some time. Then you observe. After heating in a blowpipe for a long time, you find the salt remains white, infusible and incandescent. And then you confirm that this needs cobalt nitrate test. But if it melts and sinks, then you need to perform flame test. If the white salt turns colored or yellow or some other color, it was originally white, then you have to perform charcoal reduction test. What your book says, charcoal cavity test, it is the charcoal reduction test. But here I have made the diagnosis test that you can make while heating, simply heating the salt with some fusion mixture in an oxidizing flame. If the salt is originally colored, then on heating also it will be colored, either same or different. Then borax bead test or microcosmic, not macro, microcosmic salt bead test. There are 2 bead tests that you have to do. So these are the 4 indications. Let us go one by one. Let us take a first cobalt nitrate test. Tell me what uh, mm, symptoms that you find in charcoal cavity heating test so that you thought of going for cobalt nitrate test. Yes, anyone? Rudra? What symptom you find in charcoal cavity heating test so that you think of proceeding towards cobalt nitrate test?
Sir, white incandescent.
Yes, white, infusible, and incandescent. Now, incandescent means it will give out light when it is heated. When you continue to heat, it will produce light. That is called incandescent. But you leave it, then it remains as white. But during heating, it produces light. That is called incandescent, white, infusible, and it will not melt. Then you immediately, in the same charcoal cavity, add a drop or two of cobalt nitrate. Then heat it for some more time in a non-luminous or oxidizing flame, in a blow-by. You continue with the same charcoal cavity heating test, you add cobalt nitrate and again it. What happens? The fusion mixture containing carbonate will produce the carbonate of metal. So these elements, these metal ions are tested. Alkaline earth metals, calcium, barium, strontium, and along with magnesium, zinc, and aluminum. These are the 6 metal ions which are tested in cobalt nitrate test. These are not confirmatory, but students, they get ready-made knowledge, information, first-hand information from this cobalt nitrate test. If it is magnesium, then this magnesium carbonate will be, because you are heating, finally it will be forming magnesium oxide. Then cobalt nitrate at the same time will be producing cobalt oxide. This cobalt oxide, magnesium oxide form a double salt. If so, because cobalt oxide is amphoteric, you can write down magnesium cobaltate, or it is very good to write as a double salt, MgO.COO. You can write magnesium cobaltate. Similarly, same thing, if it is zinc oxide, then zinc oxide and cobalt oxide will give you zinc cobaltate or cobalt zincate, because both are amphoteric. So it is better to write ZNO.COO. This is called Rinman's green. Either you can write zinc cobaltate or cobalt zincate, nothing. Similarly, aluminum salt will give you aluminum oxide and cobalt nitrate will give you cobalt oxide, a double salt. This is called Thénard's blue. It is a blue color, but it is called Thénard's blue, and that is called Rinman's green. And you can write down mix up. You can Al2COO4, because both cobalt and aluminum, they are amphoteric. Aluminum cobaltate or cobalt aluminate, you can write down. Just add up the formula. Al2COO4 or COAl2O4. And calcium, barium, strontium, they all the three produces gray or black color, because the calcium cobaltate or strontium cobaltate or barium cobaltate, they are all black. So at least you will get either of the three will be present, calcium or strontium or barium. If after cobalt nitrate test, there is no blue color for aluminum, no pink color for magnesium, no green color for zinc, because zinc will produce a green color, magnesium pink, and aluminum blue. If it doesn't produce green, blue, or pink, it produces a black mass or gray mass, then definitely it is either calcium, strontium, or barium. So I've given a table so that. Then coming flame test. Flame, you have to convert the alkali metal, sodium, potassium, lithium. Rubidium is not given. Lithium does produce a red flame in the flame, but lithium salts are not given. So also strontium salts are rubidium salts, cesium salts are not given. So among alkali metals, sodium, potassium, and all the 3 alkaline earth metals, not magnesium. Magnesium is tested in the cobalt nitrate test. So calcium, strontium, and barium, sodium, potassium, they are tested in flame test, because salt, you first take a nichrome ware. In your book, platinum ware is recommended. Platinum ware is very costly, yes, but nichrome ware can do the job. Nichrome is a nickel chromium alloy, so that is a cheap ware. You have a ware handle, glass handle, and you make a loop around at the top. You can take also platinum ware, no problem, and make a loop and clean, not loop now. You can make a loop, but for bead test you have to make a loop. But now in the platinum ware or nichrome ware, you clean it properly by first rubbing in a sandpaper, by scratching in a sandpaper, and then putting in a conch shell in a watch glass and showing it to flame. You will find color is coming. Again, put in a conch shell, color is coming. In repeated manner, you find that no color is coming, and then you reject that conch shell watch glass, clean the watch glass, take fresh conch shell, and then add little bit of salt and make a paste of conch shell, a little bit of conch shell and little bit of salt, make a paste, and again put the tip of the nichrome ware or platinum ware and take some salt in that tip, or you make a loop. It will better to hold a more quantity of salt and show it to the flame, non-luminous or oxidizing flame. You'll find the flame color will be there because they have lower ionization energy, so they will go to the higher energy level, and while they return to the ground state, they produce a characteristic emission. That emission spectrum color is different for different metal ions. Now, sodium gives a persistent golden yellow, remains for a long time. Unfortunately, in your book, sodium is missing. Sodium is the number one, gives golden yellow color, and sometimes in other salts, sodium appears as an impurity. So that masks the original color of potassium, calcium, strontium, barium. Therefore, we look the color in a double blue glass. There are two, cobalt glass, which is a purple color cobalt glass, two at a time, two taken together, clubbed together, and look to the flame using the two cobalt blue glasses. They're called blue glasses. Actually, it's purple. So when you look, you find a different color because it filters out sodium, and the original color is so the cobalt blue glass filters the yellow color of sodium persistent present in as impurity in other compounds. So potassium gives a violet or lilac color, normal eye in normal flame, and through cobalt blue glass it will produce crimson. Sodium persistent golden yellow but colorless. Totally it absorbs. The cobalt blue glass has a power to absorb all the yellow. Another, it will send all others, but not the D1 and D2 lines. It is absorbed. And calcium will brick red, but it is very transient. So students, they get a confusion between sodium and calcium. The flame color is different. Is golden yellow and is brick red, but it lasts for a short time. But this color remains for a long time for sodium, lasts for a very short time for calcium. And in double blue glass, it looks green. That is the difference. This is colorless, this is green. If at all there is a confusion between sodium and potassium, you can confirm in double blue glass. Strontium, it is crimson and purple. Barium is a pea green, bottle green or pea green, and blue is green. So this is the flame test for different alkali metal ions. Two alkali metal ions that is usually given, but it is for all alkali metal ions. And three alkaline earth metal ions, not beryllium and magnesium, as you know. I have given all other rubidium, lithium, everything I have given in a table. Coming to charcoal reduction test, which your book says charcoal cavity test. I have made it charcoal cavity heating test as a diagnostic tool to instruct whether you are going for cobalt nitrate test, whether you are going for flame test. Flame test, what is the indication? Can you tell me, Rudra? What is the indication that you will be doing flame test? Yes. what indication you get from the charcoal cavity heating in an oxidizing flame? So that, yes,
Sir, it sinks down. The
yes,
salt
it
melts and
melts, the
sinks
salt
down.
melts and sinks. Then you perform charcoal cavity. Now, you may ask, sir, calcium, barium, strontium, they were present in both flame test as well as in cobalt nitrate test. So what will happen? They will show two symptoms. First, it will show the symptom of melting, but finally some part will remain behind. So the part which will remain behind, then you will add cobalt nitrate, and that will produce a gray mass. Immediately it will turn gray. That will indicate either calcium or strontium or barium. Then you do separately the flame test. You can distinguish between barium is pea green, flame coloration, strontium is crimson, and calcium is brick red. Very transient brick red, and which will give green color in double blue glass. Yes, green color. Now coming to charcoal reduction, that you have to make. Uh, you are just mimicking a mini metallurgy. You'll be getting in many cases metals. What do you do? Same salt fusion mixture. Already you have taken in the charcoal cavity heating test. Do it fresh. Once you know the color changes from white to other, then you are going for charcoal reduction. Then salt, fusion mixture once again, then charcoal powder. Add some bit of charcoal powder. Or of course it is charcoal cavity, but add some charcoal powder. It will be sone pe suhaga. And then heat in a blowpipe using reducing flame. Here reducing, that is why it is called charcoal reduction. Reducing flame. There is a lot of unburned carbon particles will be there. It is yellow flame, not blue. So when you heat for a long time, you will find ultimately it will form carbonate because fusion mixture will provide carbonate. Whatever may be the cation, it will form carbonate salt. Carbonates are easy to decompose to produce the corresponding oxide. And since there is charcoal powder or charcoal itself as a reducing agent, it will reduce. A mini metallurgical process will happen. You get metal. In case of lead, it will find a bead. You'll just remove it from that cavity, and you will find a bead which is malleable. You just strike in a hammer, it will be pressed. Malleability will be found, and you can just try to scratch in a paper, it will mark paper, because lead has a power of marking paper. So, and the upper part of the hole, that cavity, there will be some color. In many cases, some color develops due to oxide. The oxide remains at the top, above that bead, and at the bottom of the cavity, you will find a little bit of metal. In case of lead, you get a white malleable bead which marks paper, and incrustation, which is lead oxide, is yellow. Bismuth will give white bead, same but brittle. The only difference, it will not mark paper. So lead and bismuth, they compete. They confuse. The difference is very simple. Hammer it, it will break down the bismuth metal. But lead will, is malleable. And it will also produce yellow. Bismuth oxide is yellow. It will produce yellow when hot. And it will not mark paper. The bead will not mark paper. Copper will give red scales. They're not called bead, they are called scales. It is not be a compact bead. It will be small pieces. It's called red scales, and black incrustation. Copper oxide is black. It's not detected because the charcoal itself is black. Arsenic, no bead, but white incrustation, but produces garlic odor. Cadmium, no bead, but brown incrustation because of cadmium oxide. So I have given you a table where all other metal ions you will find in the table. And coming to borax bead test, you are getting questions from borax bead test. Borax is nothing but sodium tetraborate, Na2B4O7.10 water, decahydrate. So you have to here make a platinum loop. Platinum wire you have to take and make a loop. Nichrome wire will not solve any purpose. So if you are buying a platinum loop, we say to students, if you're buying platinum wire, then you can also use that for the flame test. But nichrome wares are available in the laboratory plentifully. We provide. I don't know what is happening today. I'm talking of decades before, multiple decades before. Then what they do, they make a loop in the platinum wire at the top, at the front far, and then dip it in white borax powder. And a lot of borax will stick onto the loop, and they sew it to the flame. Slow it to the flame for some time. It will produce a transparent glass-like bead. Glassy bead will be produced at the top. In that loop, you will not find a loop, rather a glassy bead will be there. Then you touch the salt. Take the hot bead and touch a bit of salt and again sew to the flame. So what happens when borax is heated? 10 water goes first, then further heated, you get a mixture of sodium metaborate and boric anhydride or boron oxide. So the glassy bead is due to the combination of sodium metaborate and B2O3. Now, then you touch, supposing copper salt, which is a colored salt. All the color salts are tested by borax bead test. What happens? This metaborate won't react. It will remain. But this boric anhydride, B2O3, react with copper oxide or the oxide of the metal. Ultimately, when you heat, it may be sulfate, maybe carbonate, whatever, but ultimately it will become oxide and it will react with boric anhydride to form the corresponding metaborate. Sodium metaborate will be there, already there, doesn't react, but B2O3 reacts with the oxide of the metal to form the corresponding metaborate. So the color which develops on the bead is due to the metaborate of the metal ion. Remember, metaborate, not orthoborate. And you have a table. And when you again check the color in luminous flame, this is non-luminous flame plast, then change the color to yellow flame, luminous flame by closing the holes. Then there will be a lot of unburned carbon particles will be there as a reducing agent. So that will reduce the copper 2 metaborate to copper 1 metaborate, then copper 1 metaborate to copper metal. So ultimately you get red color because that glass will be having some red copper inside and the bead color will be red in luminous flame due to the metal. But in non-luminous flame, there will be no metal, it will be simply copper metaborate. So you get a table. I have borrowed it from NCRT, but I have given a long table in my. So non-luminous flame, blue, and when it is hot, it is green, but when it is cold, it is blue, it's copper. And if you use luminous flame, then this will vanish. Then further reduction will happen to give you a red due to copper metal. And when it becomes hot, you don't see anything, but when you cool it, then you get red copper. Then it is reddish brown, violet is nickel. In non-luminous, luminous, gray. Light violet, but that will become colorless. Manganese metal will not have any distinct color, so that violet color will vanish when further reduction to metal happens. Yellow, brown, green. The ferric will be converted to ferrous. Iron metal is not formed. With a luminous flame, the yellow brown due to ferric is converted to green because of formation of ferrous, not iron metal. So here same thing I have written here, and a extensive list I have given in luminous flame in cold. Here on cold and cold, not in hot, but here hot cold, both the cases. Yes sir, I am from Puri of class X. When you came our school to teach us periodic table, oh, you are in class X, don't worry, you just see us and then say bye bye. And when you go to class 12, you will need all these things and you study. Yes, we will have a future, don't worry, keep in touch with me, we will have a future together. But now it is not meant for you. You are in class 10, it's not for you. So you can watch us. No harm. Your examination is at in a very near. So better not to waste your time. Bye-bye. See you later. Nupur, Nirlipta, Sao. Nupur, Nirlipta, Sao. Now, another alternative to this borax bit test, not in your book, but it is done. It is an alternative to borax. Supposing borax is not available, you can use micro, not macro. Microscopic salt, name is a misnomer. Microscopic salt is nothing but sodium, ammonium, hydrogen, phosphate, tetrahydrate. This is also meant for color, for detecting colors, salt, metal ions. So same thing you will do. Platinum loop, you take a lot of this microscopic salt, prepare a glassy bead. How a glassy bead is produced? The microscopic salt is heated, 4 water goes, and then further heated, it gives sodium metaphosphate, PO3. PO3 1 minus, not 3 minus or 2 minus. NaPO3 plus ammonia plus water. So the glassy bead is due to the metaphosphate of sodium metaphosphate. But when a colored salt is heated with that glassy bead, then oxide is formed, then sodium metaphosphate reacts to produce. Interestingly, this is metaphosphate, but the product is not metaphosphate, it is orthophosphate. Sodium, copper, orthophosphate. So the color that develops in that bead is due to orthophosphate of the metal, but there in borax bead test was due to metaborate of the metal, not orthoborate. Here orthophosphate of the metal color develops. You must remember, and I have given a list. A different color, a similarity is there, but different table I have given to know which metal ion gives which color in oxidizing flame. This OF means oxidizing flame, OF, hot cold, and RF means reducing flame, hot cold. So that is the end of our entire program. We have completed acid radicals, anions, and in metal ions, cations, we have seen the dry tests, dry test tube heating, charcoal cavity heating test, the diagnostic test, then cobalt nitrate test, flame test, charcoal reduction test, borax bead test, and the alternative is microscopic salt bead test. Okay, then we are coming to the most important part. Let me tell you, now I am feeling the way I have evolved this lecture, I clearly feel that I cannot complete. Oh, Nupur Nirlipta says that, sir, I had remembered all periodic table elements. Okay, that's a very, very satisfying moment for me. Bravo, congratulations. Hydrogen, helium. Were you there with me? Then you would have, maybe you would have sung with me, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, number 10, right? Nupur, are you still there? Are you a girl, Nupur, or Nupur Nirlipta, you are a boy? I can't make out from the name. Anyway, good. Yes, then let us use I will be writing something now. Okay. Pick up your pen. But I will not complete today. I will have another session, maybe tomorrow. Keep vigil onto the if you have already subscribed to my channel by hitting the subscribe button, then you will get notification. Or if you are with me, I give you in Zoom the link. Some of you are in the loop. I'll give you a link, and also I share that in my Facebook page. I will have the next session. We cannot complete, but the most important thing we'll be doing today in another 15 minutes. It's not that easy, you know. It's already 1.5 hours, more than 90 minutes gone. It's not that easy, guys, to now. What we'll be doing, separation of metal ions or say cations. I write down cations into groups. Group 0 is a single cation, just like a single element set. Group 0 contains only one, not metal ion, but one cation, ammonium ion. Okay. We'll be doing separately. Salt, we add sodium hydroxide solution and heat, or soda lime. Sometimes you take soda lime. Sodium hydroxide is better salt. You get ammonia. If it is ammonium salt, without going for systematic analysis first, finish this group 0. Add some the salts with alkali, sodium hydroxide, heat, ammonia will come out. Distinct smell, pungent smell will come out. Plus whatever it may be, we don't bother. We don't know all what are, ammonia will smell, and that will be detected by, you know, HCl, conch HCl, rod dipped in conch HCl. You get dense white fumes, which you already know, and Nessler's reagent, which is K2HgI4. K2HgI4, which is a complex, mercury complex, prepared by adding mercury chloride with excess of Ki, get potassium tetraiodido mercurate 2. Oh, then this is called Nessler's reagent. When you add, you get and then open each box and then analyze each precipitate in presence of the other systematically. Now, salt solution, which is called the original solution, OS, which is given to you, that is first treated with dilute HCl. While you prepare a salt solution, supposing only salt mixture is given, you have to prepare a solution. You try first with water, shake it. If it doesn't dissolve, then add a little bit of hydrochloric acid. Sulfuric acid is better. Add up dilute sulfuric acid. Still doesn't dissolve, you treat it with conch HCl. Still doesn't dissolve, then add nitric acid. Still doesn't dissolve, aqua regia. So there are so many, you can go up to aqua regia. So prepare a salt solution, then add dilute HCl. Then if there will be precipitate, this is called residue, means precipitate. Then group 1. Just make a pudia, group 1. The group 1 metal ions, don't confuse with group 1 do of periodic table. Hello, I remember, Nupur. It's not that periodic table. Group 1, this is analytical groups, nothing to do with periodic table groups. Group 1 contains 3 metal ions, silver, lead, and mercurous. In your book, only lead is given. I will show you. Very, very unfortunate. Group 1 contains silver, mercurous, and lead. Why? Why I will not show you now? Hello. No, no. Once again, welcome to yet another session on. Okay. Oh, okay. Then we are coming to the most important part. Okay. I was showing the NCERT book. I'll show you later. So it is given only one. But silver, lead, and mercuric, not mercuric. Mercuric is in group 2. Group 1 is mercurous. Ag2 2 plus, or some guys they write Ag simply 1 plus. Actually, as you know, it remains in a dimeric form, Ag2 2 plus. And then remove that pudia, filter it, take that white. These are all white precipitate. Oh, this is all white. All white. Silver chloride, lead chloride, because the precipitant is HCl. This is the precipitant, the chloride ion. The real precipitant is chloride ion, is HCl. Then you take this filtrate, which is a solution. Take the filtrate after filtration, that contains the rest solution. Then add another reagent. That is, you can add some dilute HCl, further acidify it, and S2S. And that is, I'll just put it in parenthesis, this is the precipitant. So group 2 metal ions are precipitated as their sulfides. So this again, this is residue that is precipitate. Group 2. Both 2A and 2B in your book, there is no mention of 2A, 2B. Somewhere it is given, but not group A, 2B together. All will come out as precipitate, sulfide precipitate. Let me tell you here, group 2A contains 5 metal ions. Lead, once again, I'll tell you why. Then mercuric 2 plus. Then copper 2 plus. Bismuth 3 plus. Cadmium 2 plus. 5 metal ions. And group 2B contains 3. Arsenous or arsenic. Antimonous or antimonic. Stannous or stannic. So all will appear as sulfide precipitate. I'll tell you the color. Color is very important. I'll tell you next time that lead sulfide, mercury sulfide, copper sulfide, bismuth sulfide, they're all black. Cadmium sulfide is yellow. While arsenic sulfide, arsenic is yellow. Antimony sulfide is orange. Tin sulfide is gray or black, gray. And then the solution, that filtrate remains the other groups. This is interesting pudia, group 2 pudia. And that next time we'll talk about how to separate from group 2B metal ions from group 2A, because they're now together. You have to use yellow ammonium sulfide and boil it for some time. Then 2B sulfides will be dissolved, forming their thioarsenate salt, thioantimonate salt, thiostannate salt, thiosalts. They are soluble. Then filter it out. The group 2A sulfides will remain as such. The 2B sulfides now dissolve as thiosalts. And then in the filtrate, add some hydrochloric acid. You will again get back the same yellow for arsenic, orange for antimony, or gray or black for tin. You get back. So by that you separated group 2A sulfides from 2B, because they interfere. Unless you separate them, you cannot detect one after the other systematically. Because I told you that presume that all metal ions are present. Today I will be telling you only the groups. So group 2 pudia is done. Group 1 pudia is already done. Then filtrate. You heat for some time to remove S2S, because a lot of S2S, Kipps apparatus has to be used here. S2S, interestingly, I learned that in many schools, not the erstwhile junior colleges, they have their Kipps apparatus. But in many schools, they don't have the Kipps apparatus outside. Kipps apparatus is kept outside the laboratory. So it is stored inside, but when it is worked, students use it, it is kept outside, because a lot of S2S comes out. If it remains inside the laboratory, then it becomes so polluting that headache will happen. So Kipps apparatus. So what they do, they take sodium sulfide solution. They prepare sodium sulfide solution. They ask to add some sodium sulfide instead of passing S2S. No, that is not correct. They get for single salt it is okay, but for systematic analysis not okay. Now the filtrate is heated to remove S2S. Then ammonium chloride is added till saturated. Ammonium chloride solution is acidic due to salt hydrolysis, followed by ammonium hydroxide. This is alkaline till alkaline. You, you go on adding ammonium hydroxide till you get a distinct smell of ammonia, till alkaline. Then, no, that's it. And I am putting a bracket here to say that this is the real precipitant. So that group 3 metal ions are precipitated as their hydroxides. Oh, by the way, after heating, you first add 2 drops or 3 drops of conc HNO3 and heat. Not only S2S will go out, but also supposing some metal ions are in their O state, ferrous will be converted to ferric. Because in this group, the residue that is precipitate will contain group 3. Group 3 metal ions are aluminium, iron, all three, and chromium. In your book, there is no chromium, only aluminium and ferric. And then you take the filtrate for the rest of the groups. So group 3 PDA, their hydroxides are all hydroxides, but the colors are different. Aluminium hydroxide is white, ferric hydroxide is reddish brown, chromium hydroxide is green. So I told you that everything is there, so it means you mixed color. You don't get any particular color. But in your book, aluminium ke liye gelatinous white, ferric ke liye it is reddish brown or brown precipitate. Chromium is not there in your book. So filtrate again is done, I'm just slanting. Then you heat it for some time to reduce the volume and again add ammonium chloride till saturated. You do the repeat same process plus ammonium hydroxide till alkaline. And then the real precipitant is S2S. So the group 4 metal ions are also precipitated as their sulfides. But that in the acidic medium, here this is an alkaline medium. Their acidic medium means to suppress the dissociation so that the Ksp of group 2 sulfides, those 5 plus 3, 8 metal ion sulfides, the Ksp is very, very small, 10 to the minus 40, 10 to the minus 50. But group 4 sulfides, zinc sulfide, manganese sulfide, 10 to the minus 12, 10 to the minus 2, 10 to the minus 15, much greater than group 2 sulfides. So for them, for group 2, we have to reduce sulfide ion concentration by a common ion effect by adding HCl so that sulfide ion goes much down. It only precipitates out group 2 sulfides whose Ksp values are very, very small, not higher group sulfides, particularly group 4. Now you have to make the medium alkaline so that we need more sulfide ions because their Ksp values are higher. Then you make, this is the residue, which is the precipitate. This contains group 4. This contains 4 metal ions. This is zinc, manganese, cobalt, all 2 plus, nickel. All are precipitate as their sulfides. Zinc sulfide is white. I'll tell you, manganese sulfide is pinkish, that's called buff colored, light pink. Cobalt, nickel sulfides are black. Then the filtrate carries the rest of the groups. You make a pudia. How many pudias we have done? Group 1 pudia, that is a perfectly white pudia. Group 2, all mixed. Group 2A, 4 of them are black precipitate sulfides. Cadmium sulfide is yellow. And arsenic, antimony, they have different yellow, orange and gray. So all mixed color precipitate is there, group 2 pudia. Then group 3, also mixed. Aluminum hydroxide is white, chromium hydroxide is green, and ferric hydroxide is brown, mixed pudia. Now group 4 pudia is ready, containing the sulfides. Once again sulfides. Then filtrate is again heated to remove S2S. And then again the same thing, ammonium chloride till saturated. Why? If you have a single salt, then why to do all these things? Why not you add the group reagent directly ammonium carbonate, you get a precipitate. Why to suppress? There is no need, there is no magnesium to suppress dissociation. Ammonium chloride saturated, then ammonium hydroxide till alkaline, and then add the group reagent ammonium carbonate. This is the real group reagent ammonium carbonate. Then the residue, which is called the precipitate, will contain group 5. That contains calcium, strontium, and barium. These three, they are precipitated as their carbonates. They are precipitated as their carbonates. White, all these are all white, not all color is same. And the filtrate is ready for the 6. Filtrate is group 6. And there is no further precipitation. The filtrate, that solution contains group 6 metal ions, which is nothing but potassium, sodium, and magnesium. In your book, only magnesium is given. Sodium, potassium are deleted, but they are in group 6. So we have made 5 podias. Group 1 podia, white. Group 2 podia. Group 2A, 2B together. We will separate them next time. Group 3 podia, hydroxide podia. Group 2 sulfide podia in acidic medium. Group 3 hydroxide podia. And group 4, that is again sulfide podia. And group 5 carbonate podia. And the rest solution is group 6, sodium, potassium, magnesium. Now, before we close, first separation of group 2B sulfides from group 2A sulfides. So, I attack kale semti kichi nahi, is nothing, no binding that you start first with group 1 pudia. Sabu pudia am pakare achi. Let us start from group 2 pudia. Pudia to separate kolu, and we will take one box after the other. Which box you take first, which box you take second, it is your job. It's your prerogative. Ame group 2 pudia taku nele ago. Then you have to separate group 2A sulfide from group 2B. That is done by the sulfides. Group 2A and 2B together, sulfides, and then add yellow ammonium sulfide, which is a polysulfide. Usually we take the symbol as S2. It can be S3, S4. This is yellow ammonium sulfide, which is a polysulfide. If it is disulfide, sulfur is -1. Trisulfide, -2/3, and so on. A yellow ammonium sulfide solution. It looks yellow. And heat it for some time, boil it for some times, you will get soluble. And the soluble group 2B sulfides are soluble only. If you filter it, residue contains group 2A sulfides. That means mercuric, lead once again, then bismuth, copper, and cadmium group 2F sulfides will remain as such. And this is filtrate contains the thiosalts of arsenic, antimony, and tin. Now, I will not write the details. I will show you. Have you written down, Mr. Rudra?
Yes, sir.
Now, I'll just show you before I leave. Separation, I have done it. No. Here. Yellow ammonium sulfide, I have written. Yes. Yellow ammonium sulfide filtrate is 2B, residue 2A. Now, what happens here? Yellow ammonium sulfide, which formula we write as NH4 whole to S2 with arsenic sulfide, will give you ammonium thioarsenate, NH4 whole 3 AsS4. Well, there is a redox reaction. Arsenic goes from +3 to +5 and sulfur from -1 to 0. Thioarsenate. Similarly, which is soluble? Thioantimonate for antimony sulfide. for thiostanate. Here sulfur is not produced, only thiostanate. So these are soluble. When you add the filtrate with dilute HCl, you again get back the sulfides, but in their higher state. It was +3 sulfide, or maybe some +5 was there, but mostly +3. Now it will be coming as +5. Don't worry. It will be same color is yellow. And ammonium, antimonate, thioantimonate will give you antimony pentasulfide, all +5. And this will be +4. Then we will be doing 2A separately, 2B separately. We have now successfully separate group 2A sulfides which are insoluble in yellow ammonium sulfide from group 2B sulfides like arsenic, antimony and tin, which are soluble in yellow ammonium sulfide. And then again adding hydrochloric acid, we regenerated the sulfides, but in their higher state. It doesn't matter. We will be needing that for our subsequent analysis. Metal by metal we will analyze. So that comes to the end of today's program, and I will give you the entire notes. You can, supposing we cannot make it, because I had a plan to finish this by 2025. Supposing we cannot make a next lecture for this analytical chemistry, this salt analysis, then you can study the individual tests from the file that I gave you. I'll give you in the description box. You can study. Or if you want a lecture very genuinely, desperately, then you can request me that yes, this next lecture you please take. I will be forced, morally obliged to take the next program. Otherwise, I think you can manage. I'm not putting any pressure to you. You can as well request me. So, how did you like it? If you guys, you are watching now or later or now later is now. So you hit, because already 2 hours passed. You are sustaining means you are really something. So hit the like button and subscribe to my channel for further notifications and videos. Bye-bye. हेलो,
Yes, sir.
ठीक है ला?